Assalamualaikum and good day. My name is Iqbal bin Zakaria, MH19068. I will present to you my project. First, I will present to you the introduction of ball and beam system. The ball and beam system is one of the most common laboratory design experiments. It is widely used feedback control system, owing to its simplicity of development and application in learning. The main components of this system are a motor and a beam, with the motor shaft assisting in manipulating the location of the ball and on the beam by adjusting the angle of tilt of the beam. Okay. The objective of this project is building a ball and beam system with MATLAB simulating software allows you to analyze the system performance without having to do an experiment. Second, to identify the transfer function and stability of system. Third, to design a PID controller to improve the response of system using MATLAB simulating software. Fourth, to improve the ball and beam system using MATLAB simulating software. Okay, this is our transfer function of ball and beam system. The variable present in the above figure represent the following: M for the mass of the ball, R radius of the ball, D lever arm offset, G for the gravity, L length of the beam, J balls of moment inertia, R ball position coordinate, and alpha beam angle coordinate, and degree for the servo gear angle. From the assumption above, the transfer function will be like this. The equation that connects the beam angle to the angle can be approximated as a linear using the formula, this formula for the equation. Okay, next, when we put this in the previous equation, we will obtain the following. The following equation is derived using the Laplace transform of the equation above. Take the Laplace transform and rearranging, we will find the transfer function like this. Okay, this is our open loop simulink. The control system in open loop control is meant to be inverse of the plan. The most significant disadvantage of an open loop control system is that it is completely reliant on calibration and is unable to adequately cope with external disturbance. This is our open loop simulink, and on the right this is the response. This is command. On the left, this is the command that we use to execute the open loop system, and on the right, this is the transfer function that we use to execute the open loop control system. The transfer function in open loop system exhibit huge overshoot, increasing the steady state values as seen by the time response. As you can see, the time response is huge overshoot. Okay, next, this is a control system with closed loop. The input is desired ball position for the plant and process. It is a controller ball and beam. For the feedback, we use a sensor, and the output is the ball position. This is how a ball and beam system may be operated in a closed loop by adding a sensor as a feedback monitoring device that sends any fault report back to the main controller via its own control loop. Thank you.
Hi, my name is Fazrul Hassani bin Kamaruzaman, metric number MH19058. I will continue to present my part, which is evaluation of time response and performance of the system. So, in this part, we will analyze the open loop response of the system by evaluating its time response performance. We will find the settling time as well as the steady state value. To do so, we will use Simulink and linear system analysis function in MATLAB. The time response performance of the open loop response will be evaluated using the linear system analyzer command function in MATLAB, as shown in figure. After we register the transfer function in the workspace, As you can see at the figure 2 in slide, we will get the time response graph in LTI viewer, which is identical to the time response graph obtained using the step common function in subtopic 2.2. As a result, a closed loop system is required to improve the system. And the figure 3 it shows the settling time of our open loop ball and beam system, which is 32.7 seconds, that can be improved. Next, I will pass to other presenter.
Hi, my name is Khalid bin Muhammad Nur Hisham. My ID number is MH19059. We will continue with stability analysis. There are two methods that we can use to determine the stability analysis of a system. The method are Pohl's and Rothe-Hurwitz criterion. The method Pohl's use the visual analysis to determine stability. If there are no poles on right half plane, the system is determined as stable. Rothe-Hurwitz criterion use an algorithm analysis to determine stability. If there are no sign change, the system is determined as stable. Using pole method, there are two ways to pull the pole zero map in MATLAB. The first one is by changing the plot type, and the second one is by using MATLAB command. The first way, using previous LTI viewer, we need to right-click on the map and choose the pole 0 in plot type. The second way is, by using the MATLAB command window, we need to run the pzmap command. By using either method, we will get the same result. Based on the same result, we can see that there are one poles on the axis and there are no poles on the right half plane. Since there are no poles in the right half plane, the system is determined as stable. Proceeding with method 2, Rothe-Hurwitz criterion, there are 5 steps: writing transfer function, determining the coefficient, Ross array table, algorithm, and observe. Step 1. We need to rewrite our transfer function in descending power of s. For example, if the original equation is 1 over s to the power of 2 plus s to the power of 3 plus s to the power of 1, we need to rewrite as 1 over s to the power of 3 plus s to the power of 2 plus s to the power of 1. In this case, our transfer function is 0.3752 over s to the power of 2. Step 2. Determining the coefficient. In this step, we need to determine the coefficient. From the equation, we have s to the power of 2 equal to 1, s to the power of 1 equal to 0, and s to the power of 0 equal to 0. Step 3. Filling the Ross array table. We will fill the Ross array table according to the coefficient as shown in table 4.2.1. Step 4. The algorithm. We need to calculate and fill the empty box. To calculate, we use the formula open bracket b times c closing bracket minus open bracket a times b close bracket over b. Step 5. Observing the sign change. In this step, any change of sign between negative and positive will result in unstable system. Since there are no sign change, the system is determined as stable.
Hi, my name is Muhammad Fishami bin Muhammad Zaki, and I will continue about my friend's explanation of this project, ball and beam system. I will explain about the steady state error performance. Okay, in this part, PP and PID controller for tracking ball position control were devised, as well as comparative examination of this control scheme. The integral absolute error IAE and the integral square error ISE are control metrics that can be used to compare the quality of regulates response from different control method or set of tuning parameters, that is ISE, to take care of the error and compare the performance of the controller. Okay, for the pole placement, the model-based pole placement control approach was proposed in this section. The controller gain was calculated using the system design specification and state space model. Okay, the overshoot of 5% and settling time of 3 seconds, the pole of the system N and K values were obtained using MATLAB command S. Okay, so we see the equation up there. Okay, now we can see the block diagram of the control scheme. As we can see also the equation where UT is the control signal, KD, KI and KP are the derivative and integral and proportional gains, and ET is the error owing to the difference between the response signal and the desired signal respectively. Proportional gain improve reaction speed, but faster response introduce a steady state inaccuracy where setting PID to obtain optimum response. The integral gain is a good solution for the steady state error. Overshoot is another undesirable response pattern that can be corrected with the derivative gain. Okay, figure on the right show a PID control scheme for a ball and beam system in which the PID controller outputs is applied to the ball and beam system, and the system output is feedback to be compared with the reference input. The goal of tuning is to achieve negligible inaccuracy. Okay, now on the left figure, we can see the board plot of the open loop system with a phase margin of 0, therefore is unstable. But on the right figure, we can see the system was stabilized using the PID controller with a closed loop board plot with a phase margin of 85. And the goal of the board plot is to estimate the closed loop system acts via a controller to the system. Next, we will proceed to the two control scheme of PP and PID were designed for ball positioning tracking control. The time response specification obtained with PID control action are 0.28 seconds for perfect rising time, 2.13 seconds for the settling time. For the overshoot is 2.86 and the steady state error is 2.2. However, superior reaction parameters of PP control action is 0.36 for the perfect rising time and 0.86 for the settling time. For the overshoot is 0.01% and the steady state error were 1.87. Last but not least, as we can see, the difference between the two performance of the control scheme. As we can see the PP and PPID, we can see the graph and the table here are showing the result. Okay, we can see the performance index for the two controllers. Okay, that's all from me. I will pass to my friends. Thank you.
Hi, my name is Muhammad Tariq Nazmi bin Abdurrahman, ID MH19055. My part is going to present the root locus. Root locus analysis is a graphical method for examining how the roots of a system change with the variation of a certain system parameter, commonly again within a feedback system. This is a technique used as a stability criterion in the field of classical control theory, which can determine the stability of the system. The root locus plots the poles of the closed-loop transfer function in the complex S-plane as a function of a gain parameter. The open-loop transfer function of the plane for the ball and the beam experiment is given as shown. The design criteria for this problem are: first one, settling time less than 3 seconds, and the second one, overshoot less than 5%. Open loop root locus. The main idea of the root locus design is to estimate the closed loop response from the open loop root locus plot by adding zeros and or poles to the original system that is adding a capacitor. The root locus and thus closed loop response will be modified. Let me first view the root locus for the plane in open loop. I will create an M file with the following MATLAB code in order to model the plane and plot the root locus. Now, after running the M file, and we will see the following root locus plot in the left section. As you can see, the system has two poles at the origin which go off to the infinity along the imaginary x. The design criteria can also be plotted on the root locus
using the sgrid command. This command generates a grid of constant damping ratio and natural frequency. The damping ratio and natural frequency were found using the following equation, which relates with them to our percent overshoot, that is PO, and settling time, that is TS, requirements. The figure shows the area between the two dotted diagonal lines represent location where the percent overshoot is less than 5%. The area outside the curved line represents location where the settling time is less than 3 seconds. To bring the root locus into the left-hand plane for stability, I will try adding a lead compensator to the system. Next part is a lead controller. First order lead compensator tends to shift the root locus into the left-hand plane. Now, let me add the controller to the plane and view the root locus. I will position the 0 near the origin to cancel out one of the poles. The pole of our compensator will be placed to the left of the origin to pull the root locus further into the left-hand plane. Add the following lines of MATLAB code to the M file, and then run the M file in the MATLAB command window, and you should see the following. Now, the branches of the root locus are within our design criteria as shown at the right section. Now that we have moved the root locus into the left-hand plane, we may select a gain that will satisfy our design requirement. We can use the rlogfind command to help us do this. Add the following as shown the code into the M file, and you will see the MATLAB command window, something similar to the following after you have run the file. The last one is plotting the closed loop response. This value of Kc can be put into the system, and the closed loop response to a step input of 0.25 meter can be obtained. Add the following lines to the M file to perform this analysis. After run the M file, and we have to select a point on the root locus similar to the selected point. The step response should look like the following shown at the right section. From this plot, we can see that when a 0.25 meter step input is given to the system, both the settling time and the percent overshoot design criteria are met.
Now, I will continue to present the last part, which is PID controller. In a control system, a PID controller is typically used to improve the steady-state error or transient responsiveness. We will be using the trial and error method to add a PID controller to our ball and beam system in order to improve our transient responsiveness and steady-state error. As you can see the picture in the slide, we can see the block diagram of a closed loop ball and beam system after adding a PID controller. Next, I will explain about characteristic of PID controller. So, number one is proportional gain, which is lower the rising time. Next, integral gain, which is eliminate the steady state error, while derivative gain is improve the system stability, reduce overshoot, and improve transient response. The figure in the slide shows how the PID controller works in a closed loop system. Next, I will continue to show the response of PID controller in our project. As you can see in the slide, the figure which is our command in MATLAB. By referring to this figure, the rise time is 0.25 seconds, the overshoot is 5.04%, and the settling time is 2.66 seconds. So, the system is stable, but the overshoot is much too high and the settling times needs to go down a bit. Based on PID table, we can increasing the KD to decrease the overshoot and the settling time slightly. Now, the figure shows in the slide, after playing with the gains a bit, the following step response plot can be achieved with Kp equal to 20 and Kd equal to 40. Finally, our ball and beam system can be claimed to be effective and stable with the steady state value of 0.25. Lastly, after we combining this transfer function into our system, we can get a transfer function as shown in the picture in the slide. Now, I will pass the presentation to my friends to conclude our project.